Hey everyone, welcome. How's it going? How are we doing? So, today, just my levels there. Right, let's just sort my phone out. But only, bam. Right. So, last stream was investigating why our BVH that was being generated wasn't that good. We found out the problem. Right, so let's open up this one, then we'll run the game here. Okay, so the last time our BVH, our top level was really bad. Like we basically had, see here there's two boxes, right? One box is there and the other box is here. So they sort of like overlap a little bit. This is fine, right? You expect this little bit of overlap. But the way we used to have it is used to be one whole box inside of the other box. So as you go down the tree, you expect them to be yeah. What was it? Yeah, so effectively if you shoot a ray and hit, you're more likely to hit both of them if they sort of overlap more, right? So it's trying to reduce the overlap. But for some reason, it made it slower. And I don't know why. So I want to sort of investigate that, but also see if we actually fix the problem. Because there's a bit of an issue. Whereas we go all the way in. Yeah, this one has a child one, but it's empty, so that's a bit weird. What's the other thing? Sometimes you end up seeing empty. Yeah, sometimes you end up seeing another ball in there for some reason. And it's like you shouldn't see more balls. Right, that's illegal. So, very weird. Hey there, Pill, how's it going? Welcome. So, we're going to be looking into that today, and we'll probably write some more debugging stuff, so you can basically trace a single ray and see what boxes it hits, and just see what improvements we can make. I also put some stuff on the Discord. Basically, there's like a plan of like what we want to sort of like achieve in the sort of next number of streams. But there's also ways we can improve the traversal code, which is actually going to give us speed improvements. But I don't want to apply these yet because I'm comparing. Right now we're working on BVH construction quality, so we want to see. We want to avoid messing up those results, so we'll do these improvements later, basically. Right. So, luckily, thanks to NeoVim, you can basically, it keeps your undo buffer, right? That's not really that revolutionary in 2023, but it's a great feature. I do like it. So, if we sort of just undo, okay. So here's our numbers, right? 1.4 ms to ray trace these spheres, right? Obviously, we're trying to make this much better. If we undo the sort of fix that we did to make the quality better, which should have given us better traversal, right? If we undo this, gotta be careful actually. Then if we run it, that was 1.15, right? That's a 20 or whatever it is, right? So, yeah, it's only 20% quicker, which is pretty crazy. So we've got to see why that is, and we don't get those sorts of bugs in this version either. So what I might do is I might check this version in, just in case, and then we can redo all the other stuff, basically. Yeah, I'm not sure if we get those sort of bugs again. I was having in the current one. It's very weird. Anyway, right, get status. What are we done? Okay, I'm just gonna say BVH improvements. Right, so now it's going to redo. Okay. Good, I'm struggling with my web compositor though. Compositing a surface hierarchy is a good challenge. Display window, display to workspace, to work window relations, etc. Yeah. Yeah, how much of a pain is it to test that stuff? Like, is it easy to reload? Because I find one of the biggest things that feels difficult about getting into OS development is testing your actual code is quite difficult sometimes. But I guess it's not like it's still technically operating systems, right? It's not the kernel though. But, you know, have you got a good setup so you can quickly reload and test things out? Leave you dragony. Hey. You can tell the holidays are coming because there's 5 million people in each and every store. Yeah, there's a lot of people in the supermarket today, and it's definitely that, isn't it? Like, I think people go from doing like a monthly shop to doing probably weekly or whatever shops, right? I don't know. Like, I typically do a week anyway. But yeah, it's definitely a lot more people. Right. So, what do we change here to like make it that much worse in terms of performance? So let's do a diff on the current thing. So this is the different shape, the one that actually constructs the BVH. This is not the thing with the bad performance. The thing with the bad or the worst performance was the actual sphere ray tracer. So all we did is we added an extra if statement. Sorry, no. Yeah, an extra if statement plus a bit of a calculation. And this is after every single time you've hit a bounding box. And this is to tell if we're a leaf node. I think we could, right, so if we try and move this inside here somehow and detect if we're a leaf node earlier, then it might be fine. There's an easy way to check that. You just get the left child. So the way to check it is you say, okay, if that is greater than or equal to... So yeah, so it used to just be a comparison. Now it's a little bit of an operation. I don't know if it's the branch. I'm really not sure. But anyway, so BC, BVH nodes count. Right, so if that ends up happening, it's not left. Well, we don't have to do left. We can just do BVH node index. Right. But it could just be the way the data is now, right? Investigate that. Wait, it's got to be less than. Oh, no. That's right. No. Wow. That made a speed, see that speed improvement? That went from 1.4 ms to 1.0 ms. So we've actually got an improvement over what we sort of checked in a second ago. So what we can guarantee then is this, the quality is actually better, even though we could see it, right? The performance was worse. So what was the problem is the extra branch, right? One branch that we added in the code, and it was worse. So you know, it's just weird. Let's see if we undo this again. Compile that. Wait. That's literally 0.3 ms. That's a lot. Hey there, Chris. Welcome. How's it going? It's quite easy. I run my entire compositor inside another Wayland window. Okay, you can do that. Wait, they have nested compositors? You can do that? Pretty cool. No need for a virtual machine. Yeah, exactly. That's the way around it, isn't it? Virtual machines usually. But that's cool. Sweet. I didn't know that. But can you do that in X11? Is that a thing? Is that a thing, or is this a new sort of like because Wayland's built with this sort of very modular sort of thing from the ground up? Is that way? Well, technically it's not 0.3. It's 0.2 ish. But still, it's still better than what it used to be. So the quality of the BVH is definitely better. But now we've got so if we go all the way down to the left, it goes to the left-hand side, right? Now we go all the way down to the right, does it go on the other side of the thing? Okay, so we've definitely sort of we've definitely I think we're definitely doing the right thing now. Because what happened is in the previous version that we had last stream, is we'd go all the way down to the left, and it will go down here, and then we'll go all the way down to the right, and it would just go like a little bit to the right of it, and it's like, what is it doing? So what would happen? So the quality of the BVH was worse. So the higher up nodes would end up overlapping each other, because it's a binary tree. So you'd basically, these guys, like one of these big nodes would be inside of the other one, and it was just really bad quality. But now this is much better. So what we want to do now is fix a couple of issues, right? With our sort of debugging code and see if they're actual problems or just the debugging code's written wrong. But yeah. So there's a couple of bugs, right? The first bug is we go way to the right. The last node is kind of empty, and it's like, what is this? I do actually want to get the sibling button. A sibling button's a good button. Let's get the sibling button in. So, so this is where we construct the BVH. It's got a nice, lovely function. This one, this bit thing here. This gets the sibling node. I didn't put it into a handy dandy function, so let's go and make that right. So we've already got these BVH parent, BVH child left. This is just a binary heap, right? So I've just basically stolen that from the internet. But I had to figure out how to calculate a sibling inside a binary heap. And the way you do that is this basically. If you draw it out, it makes sense. But yeah, you have to draw it out. It's just one of those pieces of code. Nested compositor is just like any other graphical program. It just runs compositor which gets input from host instead of the kernel. Right. Right. Oh yeah, surely any of the yeah, because people have also done those sort of you can connect to an X session remotely. So I'm sure like a remote desktop basically does the same sort of thing, right? So right, that's pretty cool. That makes sense. So we're now at this guy, which means we want to make another button, right? More buttons. And also, what's really weird, right, is why the hell, right, is this, what's up with the spacing here? Like, I thought I just cut left. Why is that so apparent, right? Very weird. So let's take a look into that quick, since we're going into that area. Cut left. Up top by 100, cut. Cut left B. Oh yeah, and then we did another cut and we didn't even use it. Right. Okay, so I did an extra cut. So let's do another cut, and we'll do sibling. And we'll do sibling. Easy as pie. Well, pie's not that easy. Not as easy as that. But yeah. Let's also shrink this a bit because it's a bit big, right? So, should do 65. And if you want to wait on composer on X, you can also have it. At least Western supports it. Sweet. Right, there we go. Got some nice little buttons now. So what I can do is I can just say like, yeah, okay, so that's ain't good. But yeah, so if I go like, oh, go to the left, and then go sibling. Oh ho. So there we go. It's pretty sweet. So that one's got a sibling. It's this guy, and it's empty. Interesting. You can have empty nodes, right? We've got 207 balls, right? 207 balls. That does make sense. So having an empty one. Also, why is it wrapping around something? Like, why does it even have a box? Is it uninitialized memory or something? Like, yeah. I know exactly what it's doing. Actually, no, I don't think I do. But I think I'm close to it. Right, let's put these guys out in the terminal. Let's crunch some numbers, see what the problem could be on that edge case. Well, it does every frame, so let's just roll with that. Simple ball and triangles. Yeah, definitely so, my friend. Just we're trying to make this go fast, you know. But yeah, things are going good. We're like, it's definitely an experimental phase. This, so we have taken directions where we've been like, so if it's, for instance, we've written like an occlusion buffer. We've written like, and we've done screen space tiles, which is something else we need to compare ourselves against as well. So where we bin these spheres into screen space tiles and get a small list of spheres for like a group of like 16 by 16 pixels, and that was a way that we would speed up the ray tracing. But that's not great for lighting. We found out. So we want a more sort of in-world space acceleration structure. So we've moved into doing this sort of BVH thing. So there has been directions we've taken which have sort of like been quote unquote wrong, but that's what we're doing. We're sort of experimenting with, it's research and development. And what's been great about taking those wrong directions is I've been able to test out my compiler some more, and we've actually made it work on Intel cards again, which has been pretty good. So it's all been worth it. Just I'm hoping that we can ray trace, and because we can basically get anti-aliasing when we build, like you can't see it here because we're doing a really odd way to color it, I think. But yeah, we can basically get anti-aliasing. It's a little bit more of a cost. I think it's like 50% more of a cost, but it will beat any post fix of anti-aliasing. You know, some deferred anti-aliasing, shall we say? So it's good. I'm just yeah, we're just in the exploring phase of can we make this go super fast. So BVH is apparently the best way to do ray tracing. So yeah, we're trying to make one without in a simple way as well. So see how it goes. But also as well this thing animates. You want to see something pretty cool. Let's uncomment the tea. And I'll try and take a sip of my tea. Hey. Wait a minute. Sorry, the tea is what stops it. We need to actually comment out this one here. Right. This is where the animation is. And look at it go. Oh yeah, never take it too close to the screen. It destroys my GPU, my computer crashes. But that's fine. We'll fix that later. But yeah. Anyways, if anyone has any questions, feel free to ask away. So, right. What's the next thing we need to... Yeah, was exploring like... Whoops. Was exploring like this guy. This guy shouldn't technically have contents, right? So if we have 207 BVH nodes, right? So let's get Milton out. 207 BVH nodes. How can we figure out the number of leaf nodes? Where's that at? Oh, right there. Oh, wait, it's didn't print out. Alright, this is good. Because if this is an odd number, then that's probably the issue. Well, it's not an odd number. So... Well, it's because it truncated. Well, no, sorry, it didn't truncate. It rounded up, right? So we did the round up. Okay. Where can I find out more about the C compiler? Sure. It's got a GitHub. I recommend getting latest master because I'm doing a release soon, and we're using latest master and it's fine. Yeah, soon is when I have holiday. Basically, I'm off from the 11th, so I'll be able to. There's been a bunch of stuff that's gone into it. But yeah, basically it's a C to SPIR-V compiler, and only what's in Vulkan right now. I technically have it transpiling using SPIR-V cross to other languages, but I've not tested it out. Yeah. So you can share code and structures across the CPU and GPU with some limitations, mind you. But it does work on Intel now, so ignore that one. Yeah, ignore this one at the bottom. But yeah, these are the restrictions. But yeah, it's pretty sweet. I'm not sure why we just have shading languages, but there you go. It's a very good idea. No problem. Also, if you have any questions about it, there is a Discord. if you want to sort of like ask away anything, feel free. But yeah. Okay. So why then, if we go all the way to the right, that's the number of leaf nodes. So if you've got a number of leaf nodes, which would be 207, and you've got 207 spheres. Sorry, no, 104. Okay, right, this is it. So if you multiply that by 2, it'd be 208. So with 208, you'd have just one sphere. You should have one sphere in there, right? You've got 2 spheres here. You've only got one. Like, you expect one sphere to be in there, but it's not being rendered for some reason. So that is definitely weird, but it should exist, right? And that's the reason why it's in a box, which is kind of like the size of a sphere. So we're not seeing the sphere for some reason. Right, it's probably because of the rendering code then. Right, let's just think about that. But also there's another problem. All right, actually, let's just solve this. Right, okay, yeah, makes sense. Right, let's solve that problem. So that's the last, it's the furthest one to the right. What does that mean? So it's like this one here, in a way. So it's not the first one, it's the second one. No, something's fishy there. No. Oh no, it makes sense. Yeah, there's an off by 1 error. Okay, because the way we assign our balls is, these are all the leaf nodes, right? Yeah, these guys. Okay, so the way we assign our balls is we go, okay, you get 2 there, you get 2 there, you get 2 there, 2 there, 2 there, and 2 there. So these are actually in order in an array. So the way you just calculate is you get your leaf node index, which has actually been a little bit difficult. Like, the way we initially had it is we would go from here, and that was just wrong. So we actually start from 7 now, which is proper. And then it will sort of fall back down to these nodes. It's taken a little bit of extra maths to get that right. But obviously it's causing problems. So this guy should have 1 sphere, which it does when we calculate the BVH, when we ray trace against it. It doesn't pick up on it for some reason. So the code where the problem is, wait, it must be, right? When we ray trace the sphere. So that is, right, this is the tiled one, which we still need to compare against that in terms of performance as we go. So that's where we kept the code. So spheres count take 1. There's a take 1. This is exclusive, right? It's not inclusive. So I want to delete that. Whereas this is inclusive and not exclusive, right? So we keep the -1 there. That was the problem, right? And away we go. So go all the way to the right. And voila, fixed. So there's still a 1 or 2 more. I think there's only 1 more problem with this newly constructed thing that we know about. and that is for some reason you can peer through some of them. I'm not sure we've fixed it now. Maybe it's fixed. Oh yeah, there was a different if statement that we had, which had actually made it worse. Worse performance, and that probably done extra calculations that we didn't know about. Yeah, I think we fixed it. Okay, I think we fixed it, which is fine. I can't see any more spheres through the walls, basically. Through the boxes. So it's all contained within inside the box, which is great. Okay, that's good. So what's the next thing we need to... So I want to just quickly analyze this and see if the quality is what we kind of expect from it, right? So let's just start all the way from the left. So we should... So we got anything else there? Your sibling, right? So it's in that sort of Morton curve thing. It's those two there and those up there. Yeah, that's not really the best box, but yeah, I think it ain't that bad. So this is this up here, right? So this one shows a single node, so it can show when it shows a leaf node, it just shows two. When it shows a parent node, it shows all of the contents within it, so it shows more than two. This one up here shows the different levels, right? So you've got like this is level 0. These are all level 1. These are all level 2. Right, and actually, this is a little bit wrong. This is a... right. I see that's why they're missing. Because these are actually leaf nodes. And these should actually kind of be part of this, but... No, it's fine. It's fine. That's why we got that bug then. So this just shows the different levels, basically. And they're all colored the same. So we can see it amongst this mess, basically. Which ones are part of the same level. So when you get to here... Like these guys are all sort of don't exist anymore because these are all the ones that are like these guys here, right? So the last one, right? All right, that's the last one. That makes sense. Okay. Right, so I'm happy that we seem to be kind of we don't have any bugs there, so that's good. So what I want to explore. So there is another debug feature that I want to add, but I think we'll save it for a second because I want to actually see if we can increase the performance, and then we can add it at the debug feature. So the debug feature is like we'll basically have a pixel, and we'll just follow the ray, and we can basically like follow it along all of the hits that it has, right? So if it hits it 5 times, we can just go over all of them and see the different hits, but also see all the hits at once, and just get rid of everything else. So that'll be easy to spot if like if there's some optimization we could do, basically. So we're gonna do I thought of an optimization, so let me just check this in. Whoa, thank you, Russell. How's it going? How you been? Appreciate the sub. Fix the... So yeah, how's it going? Appreciate the sub, my friend. Thank you. I'll do the Bournemouth salute in a minute. But yeah. Fix the... so fix the sort of improved, or the new and improved in the new quality pass that we did, right? So this got us, yeah, it kind of got us a small improvement overall, the quality pass, but that's fine. Right. So the performance optimization that we want to do is the following. Corona. Is that a place you've been to? I was all home from a train station because we were waiting for an hour for a bus. Makes sense. Only 5 km though. But nice. Yeah, I always like a walk. When I was younger, my dad used to offer me a lift everywhere, but I'll just walk because I put my headphones on, just listen to stuff, and it's just relaxing. You just sort of get to have a stroll and just just collect your thoughts, and walk is great. Love a good walk. Yeah, so thought of a couple of ways to improve the BVH traversal code. So one, if we hit a BVH node, so when we hit it, if we hit a sphere that is closer than the actual node, don't traverse down the node, right? It makes tons of sense. So if you've already been down this left-hand side of the tree and you've hit this ball here, but this ball, right, is closer than this node here, just don't bother when you come back up here and try and traverse this guy, just don't bother going down it anymore, right? Basically, and then you just basically have got rid of all of that traversal. So that's pretty good optimization, right? So, but to combine that and make that happen more, there's another thing, right? So when you CPUs have branch prediction, right? Basically, this is it. If we hit a left and right node, choose to go down the closest one first, right? Closest one along the array first. This makes tons of sense, right? If you hit these two, right? This node is actually closer, so I might as well. So I'm more likely to find a closer sphere here, which could potentially obstruct this box here, right? For that pixel. So that's what we're going to add, and I think we should see some performance increase, hopefully. And then we'll probably just study the code and see what else, anything else we can make better. But yeah. And also read, pretty good, man. We just fixed a problem in our BVH code. So now the improved quality is actually faster than it was before. We improved the quality and it was worse somehow. Turns out it's a bug in the traversal code. But yeah. How's things going with you? Have you had a good weekend? Right. So where are we going to do these checks, right? So we hit a BVH node, and okay, easy. So we hit BVH node here, right? And T min element is less than closest hit depth. Right, closest hit depth is the sphere that we hit. Right, so that should give some form of improvement, but to combine it and make it better, if we hit a left and right one, choose to go down the closest one first. So first of all, we need to collect both of these, right? So these are our sort of T-mins, we'll call them. So T-mins, rel BVH. Just really pack that in there and something like that. Right, so now we've got these in an array, so there's the left and right one in there. So we just choose to go down the closest one first. So after we've reversed or checked both BVHs, we want to say, okay, well, we've hit both of them. So we want to say, I'm not sure how good of an else statement it really is. It will execute both anyway, probably most of the time. Or maybe not. So we want to do another, we want to do like a select statement probably. Or like a select, right? Because we don't want to make it too branchy. We want to make it a simple sort of condition, like a ternary operator. That will hopefully not branch so much. It's just very easy to have branchy code when you retrace. There's branches everywhere. Hey, it's on a Divine Fox. Good man, doing good. Doing pretty good. It's been chilling, basically. It's been staying inside, you know. All the good stuff, looking after the baby. Do you want a single line of code this weekend? Oh no. I'm reading some stuff, can't wait to implement them. Nice. Is that with your compiler and that? Yeah. Sometimes it's good to do a bit of research first. But yeah, it's cool. Also doing pretty good. Nice, good to hear, good to hear. Working on my shader code to draw 2D objects. Very nice. Awesome. You working on a little 2D game? Working on a EU and by 2D objects, so does it mean you're rendering it purely with code and no sort of textures? You can rewrite the register allocator. Awesome. Yeah, apparently I just heard this from someone in chat when I was writing my compiler, is that no one's really solved the register allocation problem. There's still sort of there's still like edge cases that are still unsolved, basically, with that side of things. Like, basically it still spills or something. Well, it doesn't really technically need to. But yeah, compilers are difficult when you like, because you're like, the hardware has like, it has registers that are not, you know, it's not that do specific things, right? Like when you sometimes use a instruction, it like implicitly uses a register. You're like, okay. There's lots of, especially in x86, right? Well, the GUI/hard is to do right. Gotcha. There's a perfect register allocator. Yeah, I can imagine. Can't imagine. There is with AI. Oh, it is. So how do we choose if we go left or right? So you've got like your T mins, right? It's the same problem we had before. I guess we've got to say, right. So you want to basically calculate an index. Easy. So you calculate an index with a preferred. So our preferred would be, so you do a comparison, T-mins 0. So for T-mins 1, I see 0. T-mins 1. So if that's greater, yeah, so if it's greater, then our preferred is right, okay, because I'll give us 1 back. And if not, I'll give us 0, which our preferred would be left. So basically then from here on out, So you want to do your node index is equal to the next BVH node index plus not plus preferred, right? And then this one is plus not preferred, right? Just reads like English. And then this will be, so I'm not sure we need this t-mins thing anymore. I think it's just going to have too much. Like we used to keep a stack to know these jump back locations. So say you're like, oh, we've hit this box and this box, but we're just gonna go down the left for now. And then after we finish going down the left, we're like, oh yeah, we want to go back up. So to avoid sort of unrolling, we can actually just jump straight back to the first child of this guy. But we wanted to write some code which would technically improve the performance, where we can just say, oh yeah, by the way, if this one isn't closer than our closest hit, just don't bother going there and go up to the next one, which instead. But that's probably, but it uses a lot of registers. It allocates a lot of VGPRs. Because you've basically got to have enough as you have a stack, right? And the max stack is basically going to be, it depends how many balls we have, but it just adds a lot of registers, which sucks. So we probably could just comment this thing out for now. And yeah, let's comment out for now. And we can always try and add it in later. Right. So is that what Amadeus, wrong one. BVH viewer. Right, so is that what we want? Left, I think so. So that should be a speed improvement, right? We've got about 1.1 ms that we used to have. So what do we have now? Let's sync it just in case it crashes. It shouldn't do because we've got bounce checking, but let's go. Oh yeah. Yeah, she got faster. Yes. So here's the number. It's about 0.9. So it got a whole 0.2 ms faster, which means today already we've gone down from 1.4 ms to about 0.9 ms. So that's half a millisecond already. Bear in mind it was a bug that made us go up that high, but still, it's good. It's good. But off of the original terrible BVH that we'd made, that was 1.2 ms. Wait, was it? It was 1.2 ms. So we've gone down 0.3 ms overall in terms of from that one. That's good. So now we should compare it against the other ray tracer, or the one that uses the screen tiles, because that one was actually faster, right? But you kind of expect it to be faster for a simple scene, but it'd be good to see how close we can actually get to it. Because it's always worth trying, right? I'm going to go down more down to the SDF functions. I use mouse to draw a shader. Excellent. But I need to add a data type to mine. Draw 2 coordinates. Nice. Yeah, I see what you're saying. Yeah. SDFs are like really great for drawing 2D. Yeah. It's a no-brainer really. Is that B tree? Yeah, it's a binary tree. We actually do a binary heap, so it's kind of balanced. A balanced binary tree, which is technically not the best for traversal performance, because you can basically optimize it where you could probably make it unbalanced, and it could probably be great for most cases or something, but I feel like that's just going to have really complicated code and it'll just take too long to even to do it properly. And it could just end up being worse performance. I don't actually know, it's just a hunch. So I've just tried the simplest thing first. And I'm going to see if it's good enough, and hopefully it is. But it's fine, because what we can do is we can have a BVH per model instance. So this is what happens anyway. You don't have one BVH for the whole game. You have many BVHs. And you basically have different levels of BVH. So basically your bottom level BVH is all your model instances. So you have one BVH per instance. And then you have a top level, which basically connects all of the bottom levels together onto the other tree. So you have a balanced tree up top. So you have one balanced tree up top, which basically has a bunch of models at the leaf node, right? And then you basically, when you hit one of these guys with a ray, you'll go into that BVH and there'll be a new balanced tree, right? So you basically get unbalanced. This is a way of getting an unbalanced tree inside of a balanced tree system as well. But it's not really, but yeah, it exists for other reasons, not just that. But it's a good, it also helps solve that problem, which is great. So I'm grateful that exists. So let's enable this boy. The sphere Raytracer tiled. So this guy is our old version which we've replaced. We have an array of spheres per tile. We basically throw them in there in some pass before this. But it's good to compare performance because yes, it is. Right, so that one is like ridiculously fast. It's 0.1 ms. So we're about 8 times slower. Doing all this traversing down these nodes. So we should kind of figure out. We should kind of have a play and just see, just do some like obvious things and see if it helps out, right? See how close we can get to this guy. But this one also is accompanied with a tile binning, which takes about 0.05, which is still kind of fast. But we also construct a BVH, calc bounds, which is about 0.03, so it's kind of about the same anyway, so they cancel each other out. So yeah, let's see how close we can get. So if we, the first thing to do is reduce the number of registers that you use, right? The number of registers that you use is kind of important. Why is important? Because basically you've got a compute unit on the GPU. You don't have a compute unit, you have many compute units. But the compute unit will be like, hey, I'm going to execute some code. Right? And this code could be like, hey, I want to load from a texture somewhere. And then, you know, so instead of stalling this whole processor for the length it takes to get this texture read or a buffer read from main memory, what it does instead is it'll be like, okay, what I'm going to do is I want to switch out to another shader, right? And I'm just going to start executing that code. And it has tons of, it has basically on an AMD RDNA card, it has like 10, it can keep hold of 10 instruction pointers or whatever, right? So, so where does the register allocation come into this? Well, you have VGPRs, right? And you have like on, see, I forget the exact numbers, but on RDNA 2, you have, so VGPR, for those who don't know, is basically like a float 32 or a U32, right? But it's a different value across every single thread. So if you have 32 threads running in lockstep, there's 32 VGPR. Sorry, you address the VGPR with the same sort of operand, but this maps actually to a distinct register within a thread, right? So they're all next to each other in memory, or it's memory in the register file, but it's gonna like load them all into the SIMD unit. And they're all next to each other, and it'll just operate on all of them at once, right? So these VGPRs, as they're called. You also have SGPRs, which stands for scalar, and that's basically just you have a value which is the same across all of your threads. So it doesn't bother putting the same value in 32 registers. It just has it in one register, and it will just bring that into the scalar arithmetic unit, right? And it'll just operate on that one thing. So so a computer unit can, I'm not quite sure, but it's different on all hardware, but on some hardware it can basically work on, it can do one sort of VALU operation and one SALU, right? One scalar arithmetic and one vector arithmetic in a single cycle or something like that. So the problem is with the registers, right? Remember when we went back to this guy? Oh wait, what was it? Yeah, where it sort of can switch out to other shaders, right? Well, when you pause a shader and go over to another one, right, you can't get rid of my registers, right, and overwrite them. So what it does is it has a massive, essentially like an L0 cache of this stuff, right? And it basically pre-allocates it when you start up like when you compile the shader, it knows this uses this many VGPRs. So it can pre-allocate it when it brings it into the computer, and it can just allocate the registers, and then until it goes away, those registers are sort of alive, and then it gets rid of them when it's gone, right? So when you have an array of 32, that's 32 registers, right? And these are VGPRs because they're different on every thread, so it's a stack. So if I just simply reduce this to 16, right, it's half the number of registers. Do we see an improvement? This is going to be fine for this code because we don't have a 16 depth. We only have 200 and whatever, so that's an 8 depth at most, right? Because it's the power of 2, right? 2 to the power of 8 would be 256, so we should be fine. Oh, we are fine. So if we compile that, and then we give it a run. So our previous one is 0.9. What do we get? 0.7. Right, so that's a clear improvement there. So let's just bring the number down even more and just see how much of a performance increase that gives us as well, right? So, I'm pretty sure that although it is more complex traversing through this BVH than just getting a linear array of screen tiles, I do think there is a lot of problems being able to us using a lot more VGPL than we need to. And we can see the exact number. We can dig into that. So, but let's just bring it down. Let's just play with this for a minute. Let's bring it to 8, right? Yeah, there's non-overflow and crash GPU. So bring down to 8. Oh yeah, we're fine. Right, so we didn't get too much better. We got 0.6. It's kind of near 0.7. So we actually didn't get that much better. Bring it down by another half. So we seem to be bound by something else now. But it definitely helped. It was about 0.05 ms, right? But yeah, I don't think we can actually have a stack of 8 deep because that means our complexity for models would be would be 256 spheres, which is probably not a limitation that we want. But yeah, 16 is probably a good one anyway. So, okay. So we've basically got a 0.4 win already today. So what else can we do to make this thing better? All right. The reason why we're seeing double now, because we're seeing the screen tiles rendering as well. So when I'm seeing these balls here, these ones are the screen tile ones. It's rendering lightning fast. So the next thing we have is we have debugging code, right, inside the shader. So let's simply have a switch which just compiles it out. And if we can compile it out, so if we compile it out, does that get us the performance? Does it get us any better performance, right? So let's just go and find all that. So I think if we just search for the word debug, right? We've got a switch statement, sorry, an if statement here, right? This isn't fired until we drag this lovely slider here, right? Then it's fired. Then it ends up actually getting slower by about 0.9 ms. But so as you can tell, you're getting divergence in the branches, right? Across yeah, so there's two things, right? One, this has like a while loop where it goes up the tree and sees if you're part of, if you're a child or a grandchild or whatever of this node, and that way we can say we want to render these spheres or not. So there's that thing, but also there's a bit of divergence, right? Some threads in the same wave, which execute in lockstep, will actually not hit this, will not want to go into here, but they have to go into here anyway, and you'll basically be working at you'd have less threads active during here. And when you sort of go around these loops here as well, the longer you could have like one thread which needs to go up more layers than the rest of them do, and you'll just be stuck in here until all of them finish and come out. So obviously we're avoiding doing any of that when we have not dragged the slider, but it still might. Will it allocate any registers for this? Yeah, I don't know if it will, but yeah, anyway, let's just take it out and just see what happens. So if debug end. So any more debugging stuff? There's another one here. Wait, is this in the it's in the BVH viewer? This is a different one. This is our debug viewer. We don't really care about that one. So I don't think there's anything else. So let's just try that. So we're at about 0.72 ms. So try that. Right, so it appears that it did absolutely nothing, probably. There it is there. So if we just give that a run, enable. Yeah, it's about the same. Wait, there it is. It's about the same. Margin of error. Right, so right, it's interesting at least. So let's see if there's anything else. If I don't find anything where I'm like, that's obvious, what we'll do is we'll do some more debugging tools, you know. So also what you got to remember is the compiler is pretty good at optimizing. Not my compiler, but when you give it to a driver, they basically use probably use LLVM, and they basically inline every single function. So all of those optimizations that will work on inline code, code gets like really well optimized. So you've basically got to spot stuff which doesn't get caught by the optimizers. So you know, for instance, if you have something which could actually go outside a scope, the compiler's probably already done that. But it's good to still move it out regardless. But you know. Okay. So this is where obviously, you know, this is the meat of the shader, the loops. So we go over the left and right node at the same time. Yeah, so, all right. I wonder if there's a way to improve, like, I wonder if there's a way to improve this code at all in any way. This is why we calculate the hit on the bounding box. Not sure if there's a way. Hmm. This says if we hit. And this one's saying if we are, you know, a leaf node. Like, yeah, this stops it from unrolling, which is interesting. To be a variable. And this is where we go over the spheres. I don't really want to try and optimize this code because this code is the same as the tiled renderer. So, well, we actually, you know, I can make this code better all day because we still want to define our look of our spheres anyway. So I'm interested more of the traversal code, just sort of analyzing it. So we do go over like two spheres and whatever. Yeah, I remember when we had this code outside of here and we had a different if statement, it was slower. But I don't know if it was this code. It may have been the different if statement that made it go over more spheres because it was a lot more slower. If we could improve the the AABB verse Ray code even more, I'm not sure if we can though. Yeah, we can improve that. That's something because we do a lot of those. Also, we could probably change the number of spheres in the base level. But you'd have to check more spheres when you reach the root nodes. But we should definitely play around with that. And then we do all this sort of branchy code here, right? And so if there's a way to help that, that'll reduce that, that'd be great. So yeah, we hit the left. If we hit the right and the left child of the right is oh, it actually exists, right? We can actually go to it and find our preferred, and then we back up on not preferred. And then we keep going down the stack. Sorry, we add it to the stack, sorry. Then we, our next one is our preferred. Then if not, we go here. So what you could do is these two could actually be the same, because I feel like you might execute both at the same time on the same is possible. So I think this line, like, you're going to go down both anyway and just have inactive threads. So the more you can move outside of these if statements, probably the better. So I reckon you could basically have preferred out here. And then I reckon you can also just do like this. But what you have to do is you have to make sure left is preferred. So you want to initialize them. It's only when you do a hit that you really care about this, right? That's also a save. You don't do a write, you don't need to. So it's only if you do a hit that you actually care about this. Yeah, no, but you hit both. No, if you hit left. Yeah, but you don't know if you hit the right just yet. Okay, good. So you can basically make them infinity. Bit of an extra cost there maybe, but we'll see. Alright, let's see how that goes. Let's just double check quick. So we got this preferred thing. We'll go into here, not preferred, does a jump there, a increment there. Then we just do this left node of that plus the preferred, right? And it will be, the left will be the preferred by default. Okay, fingers crossed. Right, so we actually got slower, believe it or not. We actually got slower. So I want to find out if that is because... Well, we could accidentally traverse down the wrong node and it will crash the GPU. It won't crash. I think it might be because of this. But I don't know. Please don't crash. Yeah, it's actually a bit faster now. But I would expect to see glitches. Only very negligible though. Very negligible. But yeah, I also don't know if it's because of this or not, you see. Yeah, but the compiler would have probably seen that. Maybe not. A bit too complicated for the compiler, probably to optimize that. What? What happened there? Wow, moving that inside actually made it slower. Probably because it went down the wrong... yeah. Probably because it went down the wrong node. Yeah. Anyway, optimizations are not worth it there. But yes, maybe because you could probably reduce that, get a tiny boost. But could you reduce any more of this? Right. Um, like if you could initialize that properly up there, this one could probably go. Um, yeah, that branch could probably go. Yeah, I'm wondering if you can basically reduce these three down to one. With this preferred thing, basically. But the issue becomes this guy. You need to say basically saying if you didn't hit anything. Yeah, why doesn't that just go into here anyway? No, because you would have say if a hit. The problem is when you hit the leaf node, you'd have processed. Mm. Have you considered that I guess my Hogma system resources? It's actually not so bad. I've tried. I've tried to actually run it off stream, and it's still actually it's about the same number. Like it's really weird. I don't know what the problem is. I don't know. I actually don't know. There we go. Like. Yeah, so my CPU is about. Ain't that bad. OBS seems to be like quite low CPU-ish, and it's kind of just on the CPU. I don't know if it must be using the GPU, right? There's no way it could be using 7.3% of the CPU and doing 1080p stream. But it's just interesting how it's not really doesn't really take up too much of the GPU time. Yeah. Yeah, I'm not sure. Yeah, it does use the GPU, I'm pretty sure. I've got a setting to use it. But I don't know if AMD's got something more specialized for video encoding. I don't know. Strange. Um, yeah, I should probably check it again. But last time I checked, that wasn't the case. I was expecting it to be worse, and it just wasn't. Hi, Cat Payne. How's it going? Um, so yeah, I'm kind of out of ideas when it comes to thinking about any big things now. Um, like we could probably try and reduce that branchy code. There's probably some elegant way to do that. We could probably spend time, but maybe there isn't. With this guy as well. But this is obviously going to be where a lot of the time is spent is ray tracing against the sphere. Um, See, if we reduce this to 1, right? Let's just see what happens. Yeah, but it's not really going to be a good idea. It's not going to be a good gauge in performance because you ideally want to still traverse. You have more leaf nodes. Yeah, I'm wondering whether we should introduce basically twice the number of like the AABB checks. They must be cheaper than doing all of this, right? I'm not sure though. It might not be. Reverse sphere. Depends how well it gets optimized up. There's like a square root in there. There's a sub. Yeah, it's not much. There's not much. There's only like one expensive thing. A few branches though, but still not that bad. Whereas this doesn't have any square root. But you're doing more traversal. And I'm more curious if the if we would make one sphere per leaf node, would that actually make it better? So maybe we should explore that. Because if it makes it better, then we'll just have waste more memory. And we're probably gonna make our traversal code like really good, basically. So yeah, we should probably look into that. Look into spherical holes, as in like bounding spheres instead of bounding boxes, that sort of thing. Right. Hey there, Raz Musco. Raz Musco. Got it. Or using both. Right, interesting. So the thing is about the bounding spheres is bounding spheres will probably be better for spherical objects, right? But they are still problematic. But what a bounding box does. So okay, so bounding box is really bad when. Okay, sorry. Yeah, so bounding sphere is actually quite bad when it comes to horizontally sort of wide shapes or tall shapes, where the sphere is actually going to be a lot. Bounding spheres are really good when the thing is kind of squarish or circle-ish, right? It's really great for shapes like that. But when it's like a very wide thing, you basically have to take up a lot of room. So I'm not sure if the bounding sphere is a good thing to switch to. But the check could be cheaper. Cleanliness here at acceptable range. Yeah, so this just test. We could just have a very simple test. Oh, we could probably optimize it. We might be able to say, hey, have you hit this bounding sphere? Maybe not. If you haven't hit the bounding sphere, skip it and make sure the bounding sphere is always bigger than the box. And then if not, do the box check. I don't know. I'm not sure. But yeah, using both is going to be difficult though, because then it gets branchy. That's an issue with it, right? The issue if you use both bounding box and bounding sphere, you've got to put an if statement. And if you're gonna have to basically execute both of them anyway, which is not good. Like you'll probably always execute both of them. So if you're gonna execute both of them, why not do both of them anyway? at full capacity, and maybe like on all threads anyway, and maybe there's a way to sort of early out that way. Yeah. Right, so she's thinking, okay, so she's thinking it for the case of doing, because the sphere check looks cheaper, right? Because this requires, we'll have to see, we'll have to get it in there, you know, and see. But basically, I think you can do something like this, and it could actually be cheaper. Let's put in that on there. Right, because that's all you need is these lines of code, which looks less. Yeah, but we've got to make sure if the bounding, but then the bounding sphere has to be bigger than the bounding box, right? It has to encompass the box, and that could actually be a good check, I think. Yeah, we should do that. That sounds like a good idea. Right, I just need to be right back. I need to go and get some more drink and stuff, but we'll continue this afterwards. They can be fed to the underlying data? Oh, they could, didn't they? Oh, yeah, that does make sense. That makes sense. Good point. Yeah, I'll give that a go. All right, BRB. Thank you. Right, welcome back everybody. More water has been fetched. Invisible water, the best kind. So... Oh, yeah, so the suggestion from Rosmusco, our dear pal, is... could... Right, so we bound and box everything. But... it's probably cheaper if you do a Rayverse sphere, right, first. So we should create some bounding spheres and see if that would be cheaper. Yeah, so you do a Rayverse bounding sphere. Yeah, wait a minute. Let's see. Let's think about it. So what does the logic want to be? So if you hit this bounding sphere, and you don't hit, yeah. So if you hit both, you go in. If you don't hit both, okay. So that could just be an integer. That's good. So we basically. Right. Okay. Let's think about it. Okay. So we've got this sort of Rayverse. So we can make a bounding sphere from could we take it from the problem is it's encoded as min max, which is kind of a bugger. But we want it as min max. Uh, so we just need a sphere center. And right, so let's just calculate it from the and a radius, right? So this is the bounding sphere center. Let's just see if it's still faster if we did this. Right, sub 0.5. Yeah, I don't know if this is really going to be... The more I write this out, it just feels like we're doing similar sort of operations here now. But yeah, that'll get your center. And then to get your sort of radius, you pick the max element of one of them. So you do like a... you would basically do like a max element, right, from this. Yeah. So, or we could store the bounding sphere data and then we can calculate a more tightly packed one. But I just want to see if we can actually just reuse this and see if there is any like, so now we're trying to reuse it. How many operations have we got? Right, still got like one of these guys. Right, I've added sub has a dependency on that guy, right? Sub dot product. Yeah, I don't know. I think this is going to be worse. So the other way to do it is just store a bounding sphere in the node, but then we just increase. Right. So say we did this. So the test would be BVH node dot sphere. I might get some stacks out. Oh yeah. There's a couple of radius in there. So we'll drop those in here. Okay. So this is the test where we say we've not got a hit on the bounding sphere. So we haven't. Then we should do the AABB test, right? The thing is though, we still need to calculate the T min. So it does need the square root. Midpoint. Right. So that'd be your sphere. Closest point to T on sphere, right? This is an ABB check. And then that'll just be T min L element, right? So then based on this, we can tell if we've hit, right? These need to go into here. Billion, so you want to hit wait a minute, you need to hit both. Or is it just the one? Yeah, you want to hit both. So it's greater than or equal to 0. Yes, that means a miss. So you want to find your T-min on sphere, isn't it? So we only know if we're a hit. Has hit if all of this. T-min element. And this would just be like, has hit. Okay. So looking at that code, you know, there could be a bit of divergence where you'd have to, you know, some threads have only hit this. Wait, so the sphere is probably going to be bigger than the box. But it might not, it might be tightly packed. Yeah, the sphere will most probably get hit more often. But it's only if we hit it would we bother checking the box. And it should be a lot more cheaper to do it. But when we hit both, it's obviously going to be slower. But in terms of like, we're more likely going to miss a node with array than we are hit it probably. Or I'll hit stuff, possibly. It's probably good to have this check, right? But there is an extra cost, is we've now probably doubled the amount of data we're reading from in our BVH node. So we still have to populate it. You know, probably, you know, we've introduced 4 more floats. So that's something to keep an eye on. Right, so let's double check this is fine. So we say, has it here? Ray. All right, I just copied this from the other, you know, code. So this is fine. It's fine. This one's saying of hit, right? If hit bounding sphere. And see if we hit the ABB. And then on the closest one. Yeah. Looks good. So, calculate bounding, sorry, the bounds for the BVH. So, how do we do that? Well, so how do we calculate bounding sphere? So your ball. You got a ball. Got another ball. What's the bounding sphere? Well, you need I think you want to take the average position. Right, so it's that one plus that one divided by 2 gets you that. Right. And then it's just so this is just at the beginning, right? And then it's obviously just whatever. Okay, the vector is to that plus radius or whatever. I don't know. Well, it's not really because you need to do some. It's. Hmm. That's taking at the center position, right? Um. So you could do the difference, get a vector, make it normalized, right, with the length, and then you can add along that vector sphere radius. But that's obviously not good. You can take the distance between these two, add each other's sphere's radius to it. Yeah, get the length, add the sphere. Yeah, that's how you do it. They can. So you're saying you don't think it'd be worth it to have both? Hmm. Yeah, maybe. Yeah. I don't know. Perhaps right. Let's give it a go. Oh, easy peasy very much. We just use scalar block alignment. So, what does that mean? Right. Standard 140. Standard 430. This came along in or GLSL 1.4. This came along in 4.3. This is for like storage buffers typically and push constants. This one is for uniform buffers. And get ready. Yes, this one has like means vec4s or like things have to be like padded to like 16 bytes, like aligned to 16 bytes, like fields and stuff, and even arrays. Horrible. Even like array strides, absolutely horrible. This one kind of allows for the array strides, but I think a vector 3 still becomes a vector. Oh no, and it maybe allows for vector 3s to be vector 3s. Something like that. Yeah, this one means that your vector 2s get 8-byte alignment, and your vec4s still have to have 16-byte alignment, and you can still do the stuff with arrays, right? But all this is a load of crap, right? You don't want this. So, but it depends. You're supporting legacy, whereas I'm not supporting legacy. So you should think about this. There's a thing in Vulkan called scalar block alignment or block layout. It's not an extension, it's core in 1.2. So this means you could basically get C++ C alignment. So things are just scalar aligned. So they're 4 bytes alignment, everything. And it's pretty good. So you don't get all the legacy stuff. Like Perry's saying, don't support X. I'm sorry, Perry. Forgive me. Yeah. This thing is the bee's knees. Yeah? But yeah. Come to the dark side. Get rid of legacy. Thank you. Also, switch to bindless. All the way bindless. First class citizen, get rid of bindings, get rid of descriptor sets. You know, all gone. Resources are data, they're just indices. Done. How was it, mate? Good, good, good. How you doing? How's it going, Perry boy? I've been pretty good. Just been relaxing, working, streaming, relaxing, working, streaming, and exercising. Got exercise. But things going alright. Still working in X11 till the day I die. But yeah, we've got all of our balls in a BVH tree now. So we've got trees of balls, Perry. I need Game Jam games to run in browser, otherwise nobody would play them. Right. I see. I see. Yeah, it's alright. People don't have to play my game. It's fine. Those people can... Yeah, I don't know, not play my game, it's fine. Hey, good, thanks, enjoying the long weekends for the rest of the year. Nice, every Monday off and Friday for the rest of the year. Oh yeah, very cool. I'll show you my balls. 2 secs, let me just unzip this code. We're back, yeah? Alright. There's the balls. So we've got BVH viewer, so it's sort of got a tree of nodes, and you can sort of go down. Right, you shouldn't see these balls here. We've got we're rendering the old renderer at the same time. Yeah, we actually sort of have ways to debug this tree basically, and only see the balls that we need to. But yeah, it's pretty sweet. Yeah, true. Yeah. So you've got a couple of renderers. We improved the performance a lot today. Yeah, technically it was about 1.1 ms, and one down to about 0.7 ms. That's pretty sweet. Trying to see if there's other ways to do it. But yeah, we're thinking about bounding spheres right now. But I don't think bounding spheres are overall good. We give it a go though. Look at that. Program way faster than you know, ChatGPT. That was good, wasn't it? So we calculate the BVH bounds. I reckon I need to do some more atomics. So center position would be the average of those 2 points. Then it would be, yeah. So you basically just like, you sum it, right? And then you do a counter based on how much you're dividing it by, right? So Sorry. Being dumb. So it will be add. Oh yeah, Perry Boy. I have I got some time off. I'm off from the 11th. So like you, I've got some holidays. So I'm pretty happy. I decided to do the just take it all off at the end. So I'm just gonna be chilling basically. You know, probably catch up with some friends, see some family. You know. I've got like 2 weeks left. And then I got like 3 weeks off. Which is gonna be pretty nice. It's good to relax some more. It's gonna be great. Hey Tim, it's been a while. How's it going? Thank you, thank you. No, it's not contributing to Vulkan itself. But yeah. Thanks, Ray. Appreciate it. We're working on a game from scratch, ready to see. I'm just gonna undo some code so we can just see it. We're basically working on ray tracing a bunch of spheres, and we're trying to make it go fast. So we've got a BVH to sort of traverse it, all in software. So not using ray tracing. We're just using the compute shaders and just doing it in software. But we're just trying to see if we can, you know, make it go fast, and so it's usable and have tons of objects made out of spheres basically, and make them look pretty. Right now it's just the normals being rendered. But yeah, how did the stream go? Tim, thank you. And yeah, if anyone has any questions, feel free to ask away. There's tons of stuff I could go into, but yeah. Reading the message from the person banned and choose. Yeah, I know, right? That was already crazy. If you yeah, the whole stream of messages in the Discord was just absolutely nuts. It was just boggling my mind. I was like, this is a waste of time. It was just horrendous. Yeah, I'm finishing on like the 20th. Run out of days. That's work on 19th. No. Or is the 19th like a Monday or something? Oh, a Sunday. It's work Sundays? Oh. Oh, maybe. Oh, I don't know. Self-taught. Yeah, mostly self-taught. But I work in the industry now, so I get to learn from people in the industry. So it's pretty good. It's really interesting, right? When you get into the games industry, what you'll discover is there's tons of knowledge where it's like, this isn't on the internet that much. You know, you have to sort of know where to look. Whereas, but also when you sort of learn a lot from the internet, you find out a lot of people in the games industry don't know of like some things that you learn on the internet, which are kind of better in ways as well. So it's interesting. It's interesting. Stream was good, working on resource management so I can build prefab support instead of a tool. Awesome. Very cool. Yeah, prefab's definitely a needed feature. One day we will be writing prefab support, but not for a while. We're currently doing some R&D into some rendering and seeing if there's something somewhat unique that we can come up with that will run fast enough and also hopefully look good. I'm still not sure how the lighting would be with all this sort of implicitly rough surface that we're going to be doing. But anyway, see what we come up with. Yeah. Okay, so we're trying to see if we can add bounding. So we're doing bounding boxes, ABBs, and it's like a binary tree. We're seeing if we could do bounding spheres, and we're trying to do bounding spheres at the same time, and we're seeing if that will be quicker. So just re-enable that bounding sphere code. So just calculate the bounding sphere. I want to see if it's better. To have 2 checks. So we'll be checking every time we go down the binary tree. We'll see if it will hit a bounding sphere first, and if it misses it, we'll just carry on. But if it doesn't, we'll test it against the bounding box as well. And if it hits both, we'll go through to the next layer. That's where it could be a problem because we check both. And also you get divergence in threads and you end up checking both anyway. So we'll see how good it actually is. But it could be good. So we're just trying to calculate the bounding sphere. So we need a radius as well. So radius would be, so I think from two spheres, the radius would be the distance between them. The distance between them plus so add the length of the distance between them plus the radius of the sphere. So each bottom level, each bottom layer, each leaf node, that's the way of saying it. Each leaf node of the tree has two spheres. So we're just calculating the bounding sphere around those right now. And then we need to go up. So it's that plus that. Right. Now you need to do some division. Where you divide by 2. Then that's the radius in it. Right. All good. So that's the bounding sphere. Now I need to take two bounding spheres and make another bounding sphere. So I think that's the same thing. Yeah, same thing. You get the midpoint. Yeah, but what happens if they're inside of each other? Right, you got two balls. They're inside of each other. Point there, point there. Name right, is it? Yeah, that's kind of good enough. Right, so you Monday was Tuesday. Oh, it's November, isn't it? I'm an idiot. Right, fair play. Well, at least it's not working the Monday. Got 2 days. Not bad. Awesome. So, how would you get the radius? How would you join two bounding spheres? I could just Google for the problem, but I'm trying to see if I'm smart enough to do it. You know, these guys, that would work because they're apart from each other, that's fine. But when they're inside, we did the distance between them. Or distance between them plus that radius. It works. It's the same thing. Yeah, but sorry, that gets you the circumference. No, sorry, the diameter. That's the word, isn't it? That gets you the diameter, which means you need to divide by 2. Right, so we just repeat that code as we build it. Yeah. So we'll do these damn atomics. Cool. And radius. We're not transforming it into Oh no, we do. Damn it. You don't have floating point atomics on GPUs, and it's the most silly thing ever. So you basically have to reinterpret cast it. Rocket science. Okay, so you've got your two nodes. So load. Yeah, so I think you're going to fetch the sibling. So the way I see it is you want to fetch sib center position x. I actually just realized they're probably called sphere, isn't it? Sphere center position. Whoopsie. Right, there we go. So basically, what are we? Yeah, let's go. Alright, which means we can delete that bit there. And we just repeat that 3 times. Y, Z, Y, Z. Another time for radius. If the radius is different, is it? Oh, shoot. Let's draw it. Oh, yeah, it's true, isn't it? Alright. I don't think I'm smart enough to solve it. Think about it. So, yeah, it wouldn't be... Oh, the endpoints. That's a good point. No, we're already finding the endpoint anyway, in a way. Yeah, but, yeah, it costs a little bit more. So you got your sphere radius. Right, so if you norm it, so you normalize vector, and you're gonna go from the other one, calculate the end. Other position, call it that's not then, is it? It's norm. So there's your normalized vector between the two. Now, Um, so the radius. So if you calculate the two endpoints, you can take the difference, and then you get the length off of that as well, right? And that will get your radius, or divide by 2, right? But I'm wondering if... Yes, it's just the center position that wouldn't be right. Okay, let's just get the two points that way. Actually, plus that needs to be a plus equals. Okay, so what you're saying is like, well, if you get the old, if you calculate the two endpoints, right? So you say, so you go, so you're going towards the new one. So you want to say previous, or like start point, which would be like essentially you want to multiply against a negated direction, and you're multiplying with your original radius, right, to get back the other way. Then you want your end position, which is the new... Wait, you need to add that to something. Should be your new radius. I need to add these to... This would be center position, whereas this one would be S dot center position. And then what you're saying is if you just take the difference, right, fair play. Yeah, then just take the difference. Wait. No, sorry. You add start point, end point. Okay. I think that's fun. Let's just see how it goes. We don't need the most fast code when constructing for this test, right? We just need to see if it actually makes the traversal faster. So now we've got this. So we've got the other. So here's the siblings ones. That'd be sphere radius. Right, so it's loaded those guys in, yeah? So we need our current and then the sibling. So you go towards the sib. So really with a sibling, you kind of want to put it into a vector. So let's do that. Yeah. So all right. That should be X there. Messed that one up. So seems good. So we need the sibling center position. Take center position. Radius. So we're updating the radius now to whatever the radius was plus. Well, it still is just that, isn't it? Oh, I just realized the other code is probably wrong. Shoot, let me correct that. Plus D. Yeah, it's definitely a simplified version, isn't it? Yeah, D direction. Oh, R2. Take that. Oh, that's pretty clever. Avoid the extra one of them. That's clever. Let me write that down, just in case we keep it. Thank you. So you've got this radius. Center position. So we've done the current center position. Sibling. Rightio, and then we just need to store it back. So this takes the current node and the sibling node, and then we'll update the locals. Yep. And then we need to store them in here. So we need this code, and away we go. All right, that should be it. What is that? Why have we got an extra store in there? Did I forget to delete that store? Because it meant to be atomics. Because of the problem we discovered with the... Because that is the equivalent of these, but not atomic, so... Goodbye. There's got to be U32s, unfortunately. It's bloody annoying, but there we go. Sphere rate. Did I forget to do a... Yeah. Right, sibling. Alright. Now it's got decode these guys, the bits from... Or bits to F32 times 3. Where's the radius? Why didn't that work? Oh yeah. Okay, so apparently it all compiles, which means it's guaranteed to work first time, right? Probably not. So I don't think we could have bugged anything else up because we've just changed data, which shouldn't. It should just make stuff not render rather than crash the GPU, I reckon. Right, so let's give this a go. Right, so it still renders just fine, but it's definitely made it slower. It's made it like way slower. So the thing we're going to try now is let's instead do a single test, right? So we can just do this instead, right? Now let's comment out all of this. So no bounding box anymore. We should probably remove the data from the BVH node for it to be a fair test as well. But yeah, I don't think this is good overall, but maybe it'd be fine. So wait, where is it? Else has hit equal true. Yeah, the compiler should optimize this, it'll be fine. There we go. So, shoot. Okay. So let's run that. So it's just in the bounded sphere check now. That's made it even slower. Yeah, it's made it even slower because it's not as tightly packed. So it's end up going into more child nodes then. But we can't really guarantee this until we viewed the we kind of viewed it inside the in the viewer really, because we can't guarantee the. But we should be able to do a simple test, right? So in the BVH view, if we just the BVH viewer, if we just do this, right? And then we can just view the where is this here? Yeah. So if we comment out all the other code, right. And then we want to do end if there. So none of this ABV, let's just use the bounding sphere. Oh, I've got it. It's duplicated. Damn it! Right, we don't have to do it the whole way. So the issue is I've actually duplicated the code. It's not in a for loop. Very smart. Float T. Oh come on! I need the max element as well. I was trying to box, isn't it? What would I want to do? I want to draw. I want to just say it's a hit. So let's get rid of all that. And we'll just say it's a hit. Boom. We'll just say it's a hit there at that level. Okay, so it's only going to render the left-hand side that way. Damn it. What? Okay, so that for a spin. These are looking quite big, aren't they? Best the brown one. That probably makes sense, actually. I need to... There's a way to stop it from rendering. Here, this is allowed. Should have really brought the whole thing over. So I think it's looking fine, right? That'll stop it from rendering. Right. Yeah, so we can just select the box that we want. What? Yeah, it's hard to really tell. I'm just ray tracing against the sphere, you see. And saying if you hit it, it's only the left one. Should we get it in on the right one as well? And instead of left, it's going to be right. Right. What? Pre-declared. Right, so now we've seen it on both the nodes, so we should be able to follow it down a bit. Why don't I see it on any of the children that we meant to hit? What is going on? So you're saying if is allowed. Yeah, I'm not sure if it's going to be faster. I think it's less precise, basically. Because I feel like, I guess here's a good. I think it's correct, right? But maybe the debug code's a little bit wrong when we go down the layers. This is much like the object is wide, right? The rendering, it's a bunch of balls in like a rectangular shape like that, and we've basically you've got a lot of this excess space which is going to bother. Sorry, it's going to actually try and those pixels is going to try and go down the tree there. So yeah, I think the bounding spheres are actually end up being worse unless it's kind of more of like a squarish kind of shape anyway, or like a spherical shape anyway. I think the box ends up being better. Even though it's cheaper to do a sphere check, basically. I think. Yeah. Alright, let's just undo that then. Well, technically, there's one more check. No. I was going to say we could have reduced the data down, but I know, I still feel like the bounding sphere is going to end up being worse in general. Alright, what did we get up to? It was here. There's a different branch of on a test layer. Maybe. I know it's just code to maintain. I'll just try again later if so. It's not too bad to mock up. Take like half hour or something. Right. So in terms of like performance, how are we looking? Okay, so something to take note of is this. Oh my days, where has it gone? That would have still ran, but what? Okay, so the one that splats it into screen tiles and then renders a small list of screen tiles ends up being quicker. It ends up being quicker because it's more complex traversing a tree, right? Obviously, than an array that's linear. That's just obvious. As it gets smaller, the tile one is still um, um, yeah. The BVH is not so bad when it's affecting less pixels either. It's not as bad as the screen space tiled one. But yeah, the problem with the screen space tiling is it's limited to like one view, and the issue is you basically have a fixed array, and it's very easy to overflow it, and you get graphical artifacts. With a tree, you can sort of pre-calculate all up front, and it scales across multiple views as well, which you're going to be having for lighting anyway. Okay. Is there any more improvements we can make to this tree that I could think of? We could quickly play around with the Z ordering. Not so Z order, the Morton Z curve ordering. Maybe like it might be better if it's one way, like a different way. Like if you swizzle it basically. Yes, to say if you did like basically mp.z. Say if you swapped x and like it's definitely depends on your model. If it's wider, it might suit a different layout. Right, so actually made it slower. Made it a little bit slower. But actually made it, yeah. So the tree that we got is just different. Tree. Yeah, this is definitely different box. But I think it might have been at the preferred settings, we don't know. Until we have a bit of a play. Yeah, that one was still worse. I think it was preferred actually because what it was X. X is the most it's the most highest set bit basically, and it goes across the x-axis in local space. So I think it will sort things better that way. And then y then z. So I think any swapping that we do is actually going to be worse. Yeah, that was only slightly worse. Okay, so I think that's, this is something to think about for sure. If we have a model that's taller, you probably want to make it so the y goes in front of z, right? But it's more depth in local space. You want to make sure z goes first, right? And that's something we definitely want to sort out there. Okay, so the other debugging tool I wanted to work on is if I shoot a ray, can I debug view what ones it hits, right? Yes. Oh, wait, there's something else as well. If we reduced it down to a single, like if you traverse the tree all the way down. Oh, we're seeing two renders, damn it. Hey Joe, welcome. How's it going? Thank you, Sleepy Mushroom, appreciate it. So we go all the way down to the left. Damn it, I thought I disabled that. Oh, did I disable the debugging in the shader? Probably true, isn't it? There we go, okay. So the thing is like our leaf node is 2 spheres in a box. It's like, is that a good number? Or should we have a box? Should our leaf node have 1 sphere in it? And then we will double the amount of nodes, right, that we'll have in a tree, obviously. Or should we have 4? Like, I don't know what is a good number. Like, the chances are when your ray passes through this box, for this particular box, you're just gonna hit 1 sphere, right? So checking both spheres when you hit this box. But the sphere check could be cheaper. But then again, if you have a different outcome, right? Look at this box; it's horrible. So after doing this check, you'll be doing 2 more checks against some boxes. Anyway, 2 boxes. Yeah, no, it's not good because you'll introduce another layer just to do 2 checks. So if anything, we shouldn't reduce it down to 1 sphere because the sphere check would actually be cheaper unless we hit it, right? So what would be better is if we can increase the number of spheres. So if we can increase the number of spheres, then that would mean, say if we hit this box and it's got 4 spheres in it, we'll have to do 4 checks. Wait, where is it? If we hit this box, we'll have to do 4 checks instead of doing what? Right? Just 4 sphere checks. Bear in mind, you could actually hit 2, right? But versus doing another box check and another box check and then 2 sphere checks, right? Because for this case, like the benefit would be if you miss, if the boxes are Like these pixels here, or these pixels here-ish, we'll be able to like skip checking these two spheres, right? But they'll still have to check these two guys. So I think it could probably be a benefit if we up it to like 4 spheres, I reckon. But maybe even 8. No, maybe not 8. 8's a bit too much. Yeah, that's another thing as well, doing heat maps. Yeah, it's a good idea. Like, there'll be a few, right? There'll be one like you're suggesting, sphere test. There'll be another one of node traversals. Or how many BVH nodes are you testing? Yeah, yeah, exactly. Yeah, those would actually be quite easy to do. So should we put those in, because they'll probably be easy, and then we can convert the code over. So they're actually dead simple. Basically add another option, and you want to say something like sphere BVH node heat map node hit. Do you want to do a node hit or a node like this is how many I've tested against, right? That you don't really care about hits. Care about hits. No, because if you hit, you would actually go down more. Go down more nodes. No, test is the same thing. Yeah. How many node tests? How many sphere tests? What other sort of heat map would you want to do? Something like that. So they're actually quite easy to chuck in. So basically in the sphere ray tracer, so in the node test is like so you're doing 2 tests here. So we've got this number of iterations. Right, number of iterations is basically it. Right. So if we have like a max, I don't know though about that. Yeah, we'll have a max iterations. And that's what I guess we'll use. Maybe you need a debug one. So why do people use Vulkan? Yeah, so if you're a beginner, like definitely don't use Vulkan. It is like really difficult. Like you're better off just going through Learn OpenGL. Tons of good articles on there and really teach you sort of like literally just go for it, getting started. Obviously you might be able to skip some simple things. And then more advanced things like lighting, and maybe you might skip the modeling thing. I don't know, and doing like advanced stuff, and they've got tons of good resources there. People tend to be using Web GPU nowadays instead of Vulkan because it's kind of like it's kind of a good wrapper around it all, but it's not got some of the latest and greatest features, unfortunately. And they have their own shading language as well, which is proper cringe. Like super cringe, mega cringe, all of that. But yeah. With Vulkan, it's basically a high level graphics card API. which you use to make a graphics API with, right? Whereas OpenGL is a graphics API, right? So you're just going to render out to the screen. Sorry. This one. Yeah. So you're just going to render out to the screen if you're doing this heat map based on number of iterations. So we could basically lerp it between blue and red. So you'll get your sort of your cold, which will select a nice ugly blue. So see, blue and red is not really nice for. Oh no, blue and red is fine for colorblind people usually. Like the most popular colorblind is red and green. Wait, that's green. And then the warm is obviously just voila. So you just lerp between that, right? So your color is the lerp between. So we go. I don't know which way it is actually. Yeah, towards warm. So you've got the number of iterations divided by the max iterations. Bear in mind, you have to convert them into a float. So the closer it is to there, it'll be closer to 1. And voila. Why you no work? Oh, I need to use the S version. Because you can have a vector of t basically. Ain't gonna work. Woo. So it's not really a good number, max iterations, for this very simple test, I guess. But if we bring it down a bit, so we could actually multiply it by 8. Might be a bit not enough, but probably do a bit more. Do 64. Bit too much there. It's not giving us what we want. I guess 16 would maybe be a good number. But yeah, so this is one sort of heat map where you're basically looking at the box traversal. We're doing a lot of traversal here, right, basically. So the other one you could do is a heat map based on the number of sphere hits. Yeah, Nvidia. Yeah, I don't know. Are they not better lately with their new sort of open source driver? Because it's more integrated into the kernel, doesn't it? But AMD's still got problems on it. On if you write shader code, if you have an infinite loop or out of bounds error, it just crashes. It's really dumb. Like it crashes your whole machine. You have to restart. Ain't good. Um, yeah, I can see the model loading being a bit difficult when you're starting out. It was like that for me as well. Just understanding it all was quite complex. You can skip it, it's fine. If you want to learn about other things, like thinking about triangles is quite complicated. It requires a bit of a maths type of brain. But you definitely pick it up as you go. If you want to learn more about like the other like parts of a renderer, feel free to just just stick with boxes. Right, you can make a game with really nice boxes. Like that's basically Minecraft. If you've seen Raytracing Minecraft, right? Um, where they've got all the RTX stuff and with really good lighting. Like most games just need good lighting, and then you basically just have a nice looking game. So you can basically just keep with simple stuff if you want to just learn the rest of it. Um, oh, it isn't made for the 1050. Fair play. Um, so I'll need to add like another thing, and this will just be like number of spheres. Num sphere hit tests. Start off with 0. It should just get compiled up. So basically, right, you come to here, and every time you come to here, you go, hey, I want to boost this variable by 1, and the computer should be like, yes, mate. And if it isn't, all your computers are broken. So basically, you else if this guy, and you're just gonna say, if I'm doing a sphere test heat map, I copy the other one, put it in here. Oh no, copied and pasted code. And sphere tests. And voila. So divided by max number of iterations, that's probably not a fair test. So what we should really do is have different numbers, where you just say sort of like, what is the sort of test max, right? It's max number of tests or whatever, right? And we'll just roll with that number instead. So I think I was looking at like 128. Seemed like a good number for that model at least. Obviously we're going to change these as we make the scene bigger and try these things out again, but for now, it's good. A number of sphere tests, 256 is probably good. Did we enable it? No. Right, so this should just render pixels that will hit against spheres only. No, sorry, that test against spheres. Sorry. It's the same, yeah. Test against spheres. So it would be the lowest level bounding box. Sorry, the lowest level. Yeah, bounding box. Let's probably reduce that to 64. Yeah, these are probably quite useful when you have a whole scene filled with stuff. And also you don't have to view the whole. If you take this off, basically, you can sort of see it. But yeah. What's the current easy peasy cross-platform GI solution, by the way? Is it still light probes in 2023, or is everyone doing SDF voxel grids now? Yeah, there's also like people doing like surfalls as well. That's another one. So like ray trace, like surfall, like surface element. Yeah. Like there's a video here that you can watch if you're like a Gen Z. You know, you can pump out a bunch of squats to it or something. I don't know. Watch a video at the same time and learn. But basically, you just put a bunch of like discs on a surface, which basically probes, right? They're sort of disc probes instead. So it's a normal and a point, and probably a radius. And you basically accumulate the lighting, so you get kind of it's accumulated lighting again. Yeah, that's another one, at least. Um. So yeah, so we could build another debug thing where we ray trace, where we sort of can individually see the hits and scan through it. This one's quite easy to build. So we could literally, okay, so let's think about it. We're adding another bar or something. Like, so basically we want another bar where we can just drag it and just be like, see the hit. And I think we'll just do the pixel in the middle of the screen, right? Is that okay? Do we want to change it? Like we just did the pixel in the middle of the screen. We could just line up and be like, oh, we hit those ones, but then you won't really see it. See the content too well, right? You won't see the balls that you're hitting. So I guess that's always the case, right? When you test a ray, a ray, so we could do a lower, or I could do a mouse coordinate. Yeah, I want to show all of them. I could just do mouse coordinate. All right, just throw the mouse coordinate in there, and that'll be a good way to do it. So you have a slider. If it's 0, you show all of them. Yeah, but then the mouse coordinate's annoying because you basically like yeah. Hmm. Yeah, I was thinking you could drag this and you could basically show each hit, right? So you can sort of have a point and you can sort of show each hit, um, and the balls that are affected. You obviously want to show the low, like traversing down the tree, hit, and then which one you test after that one. That makes sense. But it's actually quite a little bit difficult to code because there's a for loop in there. No, it could be fine. And if you hit that one, then allow. I was trying to think it's going to actually be useful. It must be, right? Because then I'll be able to actually see how it's traversing down the tree. Yeah, it's going to be useful. Let's chuck it in. So we'll just do the center of the screen at the moment. So we want to basically have a bit of input data, which is going to go into here. And the input data is going to be debug ray. So debug traverse hit index, right? So that could be num. It might have been num iterations that we saw earlier. It's probably a different game. So I reckon what we can do is we can just plug this boy in. So we need another slider. Ah, damn it. Right, so that ought to be good enough being passed in there. So the next thing to do is to actually go and use the bugger. So in our sphere ray tracer shader, we're just going to keep track of the number of sort of like, so this is traversal hits, which is different. So it's saying, hey, have you hit? Up this number for me, please. And what we also need to test is if you've got this sort of traversal hit index. Now it shouldn't be an index, it should be a number, right? What is the hit number? Because 0 is, where is it? Yeah. So if your hit number exists and if the hit number is not equal to this guy, then we basically don't want to show. We don't want to show anything from here. So we could basically choose to like just not go down anymore. But the problem is it's going to say it's a hit here. So you probably want to say just like allow traverse equal to 0, or if that, then we allow. So I can't bother to tab indent the other stuff, so we're just going to do something dumb. That's fine. I'm not doing that. and so update number of hits. If it's disabled, allow it. If it's not disabled, make sure it's equal. Okay. Right, so this is going to allow it for every single pixel. I didn't think about this. This is every single ray right now. So should we run it to see what it's like? Kind of interesting. Right, so this is disabled. And then if we use the new... Okay, so what's interesting is... That's obviously wrong. It would only work for the... Yeah, so we should show the... Well, you should see the spheres here. These are the leaf nodes. You should see the spheres. But when it's not a sphere, you should see the box being rendered as a whole. So what's going on? Oh, of course. Okay, so it's got a traverse. We've just got... We might have to keep a stack of data, you see, to do this one properly. So, if you hit the parent, or as soon as you've hit something, you want to allow all the children to succeed until you have to come back up again, right? Past the allow hit thing, right? So you want to say like an ancestor allow traverse. So basically you want to or equal allow traverse on to there. Or is it the other way around? Something like that. And you want to turn this one off when you come back up past when it actually happened. Right, catch you later. Have a good one. So if allow traverse, you want to hit. We you want to find like a depth that you hit. If you go up, is it up past that depth? So like say if you say if you let's say you're debugging this traversal hit. You want to see all of its children, right? Is that a good idea? Probably not what you want, is it, actually? Like, you probably just want to view the box, right? And then when you go to the next traversal hit, you want to hit that box. Show that box, and then so on. And then you want to show the spheres. As well. But you also then like displaying all of them at the same time. Probably not possible. Or you could. See, rendering the box is just saying where's that closest hit stuff? Here, isn't it? See, I'm not sure about the normal. So why do you need the normal? Okay, the coloring. We could just debug out. Because ideally you want the other pixels to render your path that you've taken. Because otherwise you're only seeing it for your... Yeah, it's kind of difficult actually, problem to solve maybe. So if your ray goes through, you might have to do a separate test for a different ray on every single pixel. And you test them against the boxes. If it hits that box, you kind of want to know, I guess you could just render that box, right? The first hit. And that could show all of them that ray yeah, it might be a bit harder. Let's try this for a second and see what sort of look that we get. Let's just pump in like to the right. Color, make it red. What? Is that like a E32 or something? It is, which means we can just do this. Voila. Right, it's just going to show everything, isn't it? Unless we... Right, that's interesting. That's the intersection of this. um, that's the intersection of the two. It didn't allow it to go further, that's why. I think that's gonna work. Okay, what's happening there? Right, so this is showing it for... So we're shrinking down, okay. So, it's like that heat map in a way, but then the further we go, it's only going to show these guys here, right? So that's going to show it for all of them. Do you want to render any spheres? Like, so okay, this is not obviously tracing one ray. This is for every single ray, right? But let's just carry on with this just for a second. Just hide it out for a bit. So it does the closest hit here. So it's still seeing anti-aliasing dust, basically, but So this is a way of... I'm a little confused though, exactly. So these pixels have traversed that many, basically. Kind of interesting way of viewing it. Like there's done that many iterations. It's kind of interesting. But if we also do it for a particular ray, then you could probably... So for a particular ray, if you wanted to view the whole box, or all of the boxes that you've hit, I don't know, and then maybe go over each traversal one by one, but you got to see it from every single pixel, right? That's not like... Because you could just show a single pixel and just be changing color, basically. It's not really good. So it's as if from every other pixel, you got to shoot a ray. And you kind of got to know which iteration it was. So when you drag this slider, like, you've hit... you've hit that BVH, which is actually the 7th hit, right? How are you going to know that? I don't think you can without doing a pre-pass and getting that information from maybe like a previous frame or something. But you can show all of them, and you can also show all of the spheres that you test against, right? So, wait, can you show all of them? Yes, you basically need a second ray, and you shoot that ray at that box from at that box again, basically. And then you can render it from your... You can render the debug shape from your sort of... We also have the BVH viewer, which is for debug code. And that one could just contain that. But the only problem is we won't be able to also render the spheres. So you could definitely show all of the ones you're going to hit, but not maybe each hit one by one, because that'd be quite difficult. Unless we traversed every single node. Yeah, unless we just went over every single node. Anyway. Or, yeah, you could probably do a different shader where you traverse down the whole tree, and for every single pixel, yeah, I don't think it's gonna be possible. I'm not sure if I like this view either, if it's really that helpful. Maybe it's helpful. But that's what the heat map's kind of for, so you can see it, right? Yeah, okay. Let's undo that, so it wasn't that helpful. Okay, so what is left on the things to do? Let's bring up the old shader. So there's like a list of here of stuff to do. We'll look into this and we'll maybe see if we can improve the performance a little bit more. But I'm just going to take a quick break. I'll be right back. Alright, so welcome back everybody. So I just had an interesting thought. And that is, we did some tests. So we have two shaders right now. There's one which uses the BVH for acceleration, and the other one was screen tiles, where I bin them per. So before we did this BVH, we actually ran some numbers to be like, ideally, we want to have this many tests per pixel. And this would give us this much performance, right? So if we take a look at those numbers now, and if you remember, we dragged the slider somewhere around here or something. I forgot what it was. And that was basically the max number that we had. It was somewhere around here-ish. So let's print out this number. Yeah, this was showing the max number of traversals, right? So I want to see that number, like what this sort of number is. And we'll look at my notes from the previous time, because then we can sort of see how close we were to that, and maybe it sparks some other ideas. Right, so somewhere around here-ish. Right, it's literally around 60, which is the number I was looking at, right? It was around 60-ish. I said 64 in my notes, but yeah. So if we open up my notes, BVH plan. This was an old plan. We didn't go this route, but there's some stuff here. Ray tracing 256 spheres for each pixel is about 3.5 ms at this 1280 by 960 weird resolution. So ideally, like, this was like saying if we could spend less than 1 ms. Oh wait, to build a BVH. Oh yeah, so we have completed that. Right, we aced that. And then if you ray trace 64 spheres per pixel, it's about 0.9 ms. Right, this was the guess. Turns out, we're kind of doing that. Yeah, but it's not per pixel. It was worst case, wasn't it? Yeah. But it's about 0.7 ms or something like that. Including like traversing the tree as well. Yeah. It's interesting. Yeah, because we look at that. So we show the heat map with 64 meaning red, right? The number of iterations. So if you do the number of iterations, that's not tests, right? That's a number of... Right, we need to times that number by 2. Thinking about it. Yeah, there's always 2 tests per level. That's a more realistic number. So yeah, it's getting pretty red here. Obviously we've hit some spheres here, so it's early out. But it's not really a big part of the screen, and it's taking 0.7, which is kind of interesting. But yeah. So the traversal is definitely having an impact in performance. Literally traversing. Okay. So what we have up for, is investigate the generation and why they overlap a lot. I think we've solved that now, right? We also want to test higher quality models and see how they perform. Going puzzle working again. Awesome. Whoop whoop. Whoop whoop. What am I getting? So we could still investigate performance a little bit more. We could also just try upping the number of the resolution and seeing what we get. Interesting. Could we make a more compact BVH based on the camera frustum to use for the primary ray? I'm not sure if I fully understand that. So you've got the camera frustum, right? You got your BVH, your tree of BVH nodes, right? So what you're saying is right on the frustum on the near plane. I see. Yes, you're saying compress it down into a 2D one. That's interesting. Like flatten it into a 2D. Like the problem is this is specific for this view, but you'd probably have to do it for each view. If we did this, it depends. Yeah, you would compress it as well. Yeah, I was thinking you could compress it, compress it anyway to like a U16. Like you can convert to fixed point. But yeah, and also be 2D as well. So the other issue as well is a model is probably going to be rotated. So the BVH will be in local space in the future. So when you do your ray, it's actually going to be translated. So this will be axis aligned and you're approaching it from this angle in a way. Well, not really. But yeah, it'll be axis aligned in local space, right? So with this version, you would have to flatten out all the bottom levels as well. So you could definitely do the top level like this, right? You could produce a flattened top level, but when it comes to the bottom levels, so the mesh instances, or sorry, the model instances, you would just have to take the outer bounding box of that, put it on the screen. Yeah, so what you're saying is make effectively like a 2D version of it. You would get a lot of overlap though, right? Would you? Yeah, So you're saying like just, right, box is over. So one, the box won't convert from world space to screen space 1 to 1, so you'd get wastage. There'd be even more, be less precise even more. Um, which means you'll probably traverse through more of them. Um, yeah, I know it could work in some way. I'm not sure though. Hmm. Yeah. So this would go on screen space. So you would do something like that, right? So these pixels will go inside it, and then these pixels here, with addition to these guys, will look inside, right? Even though they didn't have to. Yeah, I'm not sure if that's really going to help. Why does it get so bad when it's so close to the camera? Is it possible to have some kind of alternative to handle it? Yeah, I'm not sure why it gets so bad when it gets close to the camera. That's something to definitely find out. I've probably got to test off stream, or maybe we just got to analyze the code a bit on stream and just figure out. Because the problem is, yeah, maybe we got to find it off stream then present the answer. Yeah, if we move any closer, it will crash. um, but yeah, I'm not sure about screen space. So the thing that makes the screen space list of spheres so good is because it's a linear array of spheres, probably, and you're just going over those. Whereas this is a tree, is a binary heap, and you're traversing over that tree. Um, and you run into the same problem, screen space, is when we bin our, we basically have to pre-allocate per tile. Actually, no, would you? No, you should have a screen space BVH, that's what you're suggesting, isn't it? Yeah, maybe not. Yeah, screen space BVH. You would just reduce the amount of data, and I'm not sure how much we're bound by that. Um, so a good test might be, yes, there's something about my BVH nodes as well. So they're this size, right? Or they're 6 floats. Or 6 ints, whatever way you want to, right? So that's, you know, so they're basically half, they're just under half a cache line, right? Um, and what's kind of interesting is this is 0, this is 1, this is 2. We skip 0. We check 2 at a time. Technically, they are going to exist in different cache lines. If it's 64 bytes on the GPU, I'm pretty sure it is. Or do they have, I don't know, maybe it's something to think about. If we literally just up this number by 1, up them all by 1, when we index them in the array, and then pad this out to be 64 bytes. Does that improve our numbers? So we did this. That made it 0.7275 if we did that. About the same. So we've padded it out to like a cache line now. So so our BVH nodes, when we make these guys, we just make a buffer. This buffer allocates a whole block of memory, which is probably aligned to a cache line, we hope. I'm not sure though. But it allocates a new block using the Vulkan allocation stuff. It doesn't do anything smart. So I would assume that it's aligned to a larger size basically than a cache line. So when we sort of put them into this array, where do we do that again? Count bounds, right? So we put them into this array. If we just added 1, Right. If we just add 1 to them all, like, would that be better? So we have to, this is when we store it. Let's try and read it. That shouldn't exist. Right, so here's where we read it. We just say 1 plus. And here's the BVH node traversal 1 plus. Sorry, BVH viewer, the debugger. Right, so we've gone full circle now. The problem is with the count. It's fine. Right, so let's give this one a go and see if it ends up being better. Right, so that actually made it probably a bit worse. It's not really made it any better. So aligning these to like a cache line doesn't seem to be anything that GPU is really concerned about this particular problem. And I'm not really sure if GPUs have the same sort of CPU cache line. I think some do, but I'm not quite sure. So that hasn't made a big difference at all. So let's try and compress the data down a little bit. So we undo all that. Could we compress this down? Right, so So if you had, so we have 6 floats. You could probably bring down to like 3 floats if you quantize it down to some fixed point range. You know. Mm-hmm. So if we reduce it down to say, you probably. So it was usually seen we're at 65,000, then you divide that by 2. That's sort of two steps. Divide 2, so that's 4 steps. So so that would be so 4 steps, then 8 steps, then sort of 16 steps. So if you have a world size of 4,000 by 4,000 by 4,000, you could probably get away with 16 sub-steps with fixed point. But yeah, so you probably do negative 2,000, positive 2,000 or something. And I'm not sure how much better it's going to be, but we could try it. We could just fix everything. Let's not bother trying to like. Let's just grid align it, and so it will snap. But let's like literally get rid of one of these, and we'll just call it bounds. Just 3 integers, unless we're just half the size of the node. And let's just see if it's any better. So the way we'll calculate it is so you just do bounds XYZ. This is gonna be horrible. So you're gonna pack it. So you're packing. You turn it into bits. From a float. So I guess why don't we just like floor it? So you could probably just do like floor, whatever, or round. Doesn't really matter. Round, and you could probably pack and then all that with the max. Good point. Yeah, that's a good point. Very good point. So if we just simply do this, what would we see? So obviously this is when we set up initially. So we've got to do it when we traverse up the tree and build the BVH. So you got to unpack and then repack. Oh, did I do shift left 32? I did, didn't I? What a booger. Alright, I'll fix that. Right, thank you. So, yes, we've got to unpack it here. So let's write some unpacking code as well. So, you do your atomic load. I guess. Alright, we'll just do this. Bounds. Bounds. We'll just load it twice. I'm not really fussed about this part of the performance, to be honest. These guys, you need to shift right 16. These guys, you want to just AND the first 16 bits or whatever. We don't need that bits to mumbo jumbo anymore because it's not gonna go to a float instead. We just want to cast to a float. Actually, think about it. Then we get the value, and then we do the min-max type of thing, and then we just store it back in there again. Excellent. So that'll build the BVH. The next thing is to actually change the code where we calculate the min-max. So we'll just rewrite the code again. It's fine. So we'll calculate the BVH. So I might disable the Raytrace, the BVH viewer code. We have to convert it twice. I don't know. It might be fine. You know, it might not be so bad. So it's be like bounds, bounds, bounds.x, shift right 16. But that's one you convert into a float, another you convert into a float, and another. Yeah, I can just copy paste this around even better in a bit. And a max. Max is AND 0xFFF. Okay, so you should just be able to copy this to the other guys. So there's one. So it's BVH left. And the other one. Which is BVH right. So obviously it's going to be really janky and align to like a whole unit. But it will be enough to test the performance at least. Shoot. What can we use as the value then? Crap. Oh no, we'll still put infinity in there. Yeah, that'll still work. It's no longer called min. Call it bounds. So we're also writing less data out maybe. And we start do the so less atomics when we build could be better in that sense. Right, hopefully this doesn't crash. Let's see. Right, they only show up in the top. And this is showing here because I'm actually rendering the old one. So let's disable that. I'm rendering the old tiled. Okay, so we won't see anything run now. Okay, it's pretty cool. We can see it here. Actually, I do want to. Yeah, we should already be using signed numbers. So when we fish this thing out, so the problem is being clamped down. Right, I got it. So when we pack it, so we load a U32, shift right. If you turn it back into a signed number first, and then you tell it, and then you, turn it to a float, that will keep the sign. So that's when you extract it. But when you store it, you, what do you want to do? Right, turn it into a float, into a sign number first, and then a U32. I'm not sure how much. I think that makes sense. No, maybe it's not sure. But definitely when you extract it out, I think you need to do something like that. Right, so let's quickly find that. You need to mask the max value. So the min isn't filled with assigned bits. Oh shoot. For the max. Ah. Right. Not sure. So the min isn't filled with assigned bits for the max. Oh, I see what you're saying. Yeah, I want to do this. Yeah, whoops. Whoopsie. Gotcha. Right. Good point. Bit packing 101. Good point. Parent node index one. Yeah. Right. Excellent. Okay, so we need to do that on the load as well. Let's find them bounds. So we need to turn it into a shoot. S32. Bugger. Good night, Officer Red. Good to see ya. Have a good night. I'll good rest. Have a good start to your work week as well. I'll see you in a future one, probably Tuesday. Later. Right, fingers crossed. This will work. Oh, bugger, I've got too many brackets. Not enough closed brackets, that's the problem. Righty-o. Oh no. What? Close the other one over here as well. Okay. So let's take these. We'll go and fix them up. So right becomes left. that as well. And then left becomes node because we've got it in a loop here and it's better. Right. That should keep the signedness and it should be enough for our test, basically. Maybe not. We've buggered it. What do we do? So X, Y, Z. Signed 16-bit integer. Damn it. We don't have 16-bit. We have to do manual sign extend or whatever. Crap. We don't have 16-bit integers on the GPU. So we can't leverage the fact that we're packing it down. Yeah. So, all right, here's going to be the test. We're going to undo that. And we're just going to see what number we get when we put it. We'll just look at the numbers. There we go. All right. Okay. So we're literally going to leave it close to the screen. Right, so got about 0.6 ms there, right? Traversing that. So if we now undo it all and put it in the same place, basically that's going to be the test. Right, so we have twice the number of things there now. So 0.6 ms to beat, so somewhere like there, yeah? It's actually about the same, 0.6 ms. So we don't really get any benefit from reducing the amount of data. So why not git stash? That's a good point. Stashing is probably better, but yeah. I'm not that good at git on the command line, to be fair. Yeah. So I'll have some more of a think off stream about this traversal code. Maybe there's something that I need to, like today we've come up, we've implemented this, for instance, where if we hit BVH node, if we've hit a sphere that's closer, don't traverse down it, right? And if we hit both the left and right, choose one which is closest and go down that one. So we've implemented that today and it has shown an improvement. And just quickly, I want to prove that it does actually work. So this should get slower if I change this Boolean conversion around. Where is it? This one here. This chooses the preferred route, so we change that to the other side, the other comparison. Yeah, that went to 0.9 from 0.7, so it definitely does help. Yeah, so if I could think of ways where we could reduce A, the amount of branching, and B, the amount of nodes we traverse, we might, or probably do some more of this next stream. But next stream, I want to I want to experiment with having 4 spheres on the leaf node, because that's going to get rid of a layer, right? Get rid of a whole layer at the bottom, so there will be less nodes to traverse down. But you're doing more sphere tests. But sphere tests are technically cheaper, but like they could technically be cheaper if they all yeah, they're technically cheaper at the beginning, but the problem is if 1 or 2 threads want to carry on through and go down the more expensive path, then the rest of the threads is going to go through there in an inactive state and not be used for anything practical. So definitely something to play about with, but it's good to have it as probably a number that we can actually just configure rather than having like times by 2 everywhere, for instance. So it'd be good to try that out. But yeah, after that, we probably want to just test higher quality models and maybe have yeah, test higher quality models probably. And just see if we can judge like how many spheres that we're gonna render on a scene, basically. See what sort of like quality we could go for. Yeah. Righty-o. So I'll probably commit this now, and then I'll upload that to the GitLab for those who have access to that. Right, so let's find someone to raid. So I'll next be on Tuesday at 6:30 PM GMT, and then what else? And then also stream on Thursday as well at 8 PM GMT. Let's read this guy. Right, thanks for coming everyone. I hope you have a good start to your week, your work week, and I'll see you guys in a future one. Alright, catch you later. Bye-bye. Alright, in a bit.